All right, this is section 8.7 in chapter 8, geometry, which is non-Euclidean geometry and fractal geometry. Excuse me. I'm going to be focusing just on the fractal geometry portion of this section. So fractal geometry is the study of natural shapes. Before fractal geometry, mathematicians thought that creating realistic natural shapes was impossible. For instance, I cannot create a tree with a cylinder as the trunk and a sphere as the top. It doesn't look natural. It looks man-made. So what happened was a whole field of study, which is called fractal geometry, came into existence in the 1970s, and it was started by a man named Benoit Mandelbrot. So it has been gaining attention ever since, and in fact, Hollywood utilizes fractals to create CGI natural landscape. So it's a very important mathematical concept, and to understand it, we're going to have to understand the three dimensions in which we are familiar with first, because fractals fall in between dimensions. So it's really a wild concept. So let's check out our Euclidean geometry. So this is a geometry that we're used to. So a no-dimensional object is just a point. So here is point A, and let me actually use a pen that works. So we have point A here. So point is just a representation of some place on the plane. It lacks dimension, which means I cannot measure it. Okay, so that's no dimension. So let's go up to the first dimension. So in the first dimension, an example of that would be a line segment. So I have point A, point B here, and I have a line that connects the 2 points. So I can measure its length. So I can measure that off. So for instance, we could say it's 5 feet or something. That would just be an example. An example of a two-dimensional object, now we're in the second dimension, would be a square. So if we measure a square, we can measure its length by its width, which gives us area. So all two-dimensional objects can be described with area. So I have an example for you. Find the area of the rectangle below. So if I draw a rectangle here, and let's make this side 3 feet and this side 1 foot. So to find an area of a rectangle, I have to take length times width. So area equals the length, which is 3 feet, times the width, which is 1 foot. And if I multiply these together, I get 3 feet squared. Notice I have to multiply feet by feet. So area is in square feet, square inches, square centimeters, or whatever. So now moving to the third dimension, we can use a three-dimensional object such as a cube. So we can measure a cube's length, we can measure its width, and we can also measure its height. This gives us volume. Okay, so when you find a volume of any three-dimensional object, your units are always cubic. So you might have meters cubed, feet cubed, it could be liters cubed, it could be a volume of liquid. So here's an example of finding the volume of something. So we're going to take a rectangular solid, so draw a rectangle, and then, place it off on a diagonal, and then just connect the lengths of it. And in fact, I'm going to redo mine because it's messy, so this will give you a chance to draw yours out really nice. So try to make both rectangles the same. There we go. That looks better. All right. So we have this rectangular prism. That's what it's called, a rectangular solid. So let's make the length of it, let's say 5 feet. And let's make the width of it 3 feet. And let's make the height of it 2 feet. So if I have to find the volume of a rectangular solid, the formula is length times width times height. So the length is 5 feet times the width, which is 3 feet, times the height, which is 2 feet. So if I multiply 5 times 3, I get 15. 15 times 2 is 30 feet cubed. So the volume of this rectangular solid, the one I drew, would be 30 feet cubed. And that's an example of a three-dimensional object. So all of those we are quite familiar with. But once again, this is Euclidean geometry. With fractal geometry, you are not going to have something that falls into the first dimension, second dimension, or third dimension equally. It'll fall in between either the first dimension and the second dimension, or the second dimension and the third dimension. So that's what makes fractals very special. So here are some examples of natural shapes that can be described using fractals instead of Euclidean geometry. The following images are natural objects that we can create using fractal geometry. And these are ones that exist in nature, such as a snowflake, a fern, a cloud, a galaxy, lungs, like your air tubes inside your lungs or bronchioles, canyons. I know a couple of you at the very beginning of the semester said that you love the national parks, so this kind of looks like Bryce Canyon here. Mountains, brittle sea stars, nautilus shell, sea urchin, the inside of a cavern, the stalactites or the stalagmites, baobab trees show fractal dimensions, and finally Romanesque broccoli. So all of these are fractals, and all of them can be described using fractals and cannot be created using Euclidean geometry. So they all have something in common. They are fractals. So that's what's really cool. And by the way, not everything's a fractal just because, it has some properties. So we got to determine why something's a fractal, and that's what we're going to do next. So this is objective 1, the only objective in this. What 6 criteria must be met for something to be a fractal? For something to be a fractal, the objects in the shape must be self-similar. And I will give you an example of all these, by the way. 2, the objects in the shape must have to have scaling. So there has to be a large objects and then smaller objects that look like the large object. The object must have recursion, and that's a rule, and we'll talk about what that is in a couple minutes. And the object must have fractal dimension. I kind of touched upon that before. Remember, fractal dimension is not normal. It is it's in between like the first and second dimension or the second and third dimension. And the object in the shape must have to have unpredictability in its order. And an object must be bounded infinitely. So you have to memorize these 6 criteria that make something a fractal for the test. And we're going to look at every single one of them in detail so that way you understand if you can determine if something is a fractal or not. So the first one, or the first criteria, is objects must be self-similar and have scaling. So what does it mean to be self-similar? That means that the object has to keep the same dimensions. So self-similar means it's the same object. So if it's a square, to be self-similar, the other object has to be a square. It cannot be, for instance, a circle or a triangle, so it has to be a square. Scaling. Scaling is taking an object and either making it bigger or smaller. But you have to keep its aspect ratio the same. So let's stop a minute and talk about what is aspect ratio. Aspect ratio keeps the dimensions of the object in place. So for instance, if I have 2 squares and I want to make that square smaller, it has to maintain a square. So if the original square, and I'm going to write down here, like let's say the length was 5 feet by 5 feet. and I wanted to scale it down. So my new square has to be 2 feet by 2 feet, meaning that the aspect ratio, if I divide the two, it has to be the same. So 5 divided by 5 is 1, 2 divided by 2 is 1. So the aspect ratio, meaning divide length by width in this case, has to be the same. So with scaling, the smaller pieces look like the larger piece. And by the way, fractals typically, when they do scaling, it scales down. So here's 2 examples of squares that are self-similar. Notice they are the same. They are both squares. One is not a triangle, and the other one's not a square. So they have to be the same. This square is scaled down. Notice that both geometrical shapes are still squares. And they have kept their aspect ratio. So once again, a ratio is dividing one side by the other. They have to maintain the same aspect ratio for it to be scaled down properly. All right, so here are some examples in nature. So when you look at this Romanesque broccoli, this whole entire shape, is shaped like this. So if I look at one of the pieces, like let's say, for instance, this one, this piece looks like the larger piece. And if you look at a smaller piece, it looks like the larger piece. So that's showing self-similarity and scaling. So just wanted to show you an example of what that means. And then if we look at the fern over here on the right, we have the larger piece here. And if you look at one of the branches on this leaf, it looks like the larger piece. And if you even look down smaller and scale it smaller, each leaf looks like the larger piece. So that's showing self-similarity, and it's also showing scaling down in this case. Okay, so we've looked at scaling, self-similarity. Those are the first 2 criteria to be a fractal. The third one is the object has to display recursion. So what does recursion mean? Recursion means that it is a rule that has to be applied to the object. This rule deals with the item being self-similar, and the rule can be applied infinitely. So we can continuously apply the rule over and over again up to infinity. So it's really wild and really cool. So I'm going to show you how this works on the next page. So here's an example of a famous fractal. It's called a Sierpinski triangle. And I'm going to show you how we get each iteration. An iteration is when you take the rule and you apply it. And when you apply it to the shape, you get the next iteration. So there's 5 iterations of the Sierpinski triangle. The first one we're going to call 0 because there's no rule that's applied. And then when I apply the rule, I get the first iteration. I apply the rule again, I get the second iteration. I apply the rule again, I get the third iteration, 4th iteration, 5th iteration. And I can keep on going on with these iterations and doing it infinitely, which is really neat. So for the Sierpinski triangle, the recursion is a rule that takes one iteration to the next. So the rule for the Sierpinski triangle is I have to find the midpoint on each side of the triangle, and then I'm going to connect those points together, and it'll create a triangle. Once we've created the triangle, we then remove that triangle that I just created from each of the larger triangles. So let's see how this works. I'm going to go ahead and grab a yellow marker here. So the first one, we see an equilateral triangle. So I find the midpoint on each side of the equilateral triangle. And what I do is I connect those pieces together, and I get an equilateral triangle. And I get this equilateral triangle I just kind of highlighted in yellow, and I take and I remove that. So to get from the 0 iteration to the first iteration, I remove that inside triangle. So once again, what's the rule? Find the midpoints of each solid triangle. Connect those points together to create another equilateral triangle and remove it. So let me go ahead and erase that triangle, and I'm going to go back to my purple pen here. So for the first iteration, we see that we have this shape, which if you like Zelda, that game, you guys call that the Triforce. So to get from the first to the second iteration, I do the rule again. I find those midpoints. So midpoints of the triangle, and then I remove them. So midpoints of each of the triangle that is solid that you see, and remove it. Midpoint of each triangle. And when I do that, I get the second iteration. And once again, I keep on applying this process over and over again until I can go on infinitely. So this recursive process, like I said, can be done over and over again infinitely. All right, so here's an example of something in nature that displays the Sierpinski triangle. If you look here on the shell, it has a Sierpinski triangle, which is super cool. The next example I'm going to show you is actually the Koch snowflake. So this is in the next video. So even though it's underneath this picture, it goes with the next video. Okay, so that's the first video. There's one more piece of it, 8.7 part 2, that you need to watch. I hope you guys are enjoying.